Okay, so I'm gonna whiteboard for you sigma notation. That's sum notation sometimes is what it's called. So if you've taken a pre-calc class, you should have encountered sum notation / sigma notation. Calc 1, you go a little bit into more depth into the various kinds. It almost becomes, geometric, shapes of it, but also, almost in a way, an algebraic expression of sigma notation. And then Calc 2, you go even heavier and deeper, and you see more application, applied calculus, things like that. So sigma notation, let's go through a few exercises here. And I think I've got a good balance of whiteboard here for you. Okay, there we go. All right, so we'll start with the classic Greek symbol here, which is for sigma, which essentially means sum. Okay, sigma is sum here, right? It looks like a backwards E. That's how I like to think of it, right? And then you have the start, and the start is always, for this simplified, this very easy, sigma notation example, right? J equals 1. That's the start, okay? And then the end, where you want to get to is N. Okay, and then so for this, we would write the expression here that J equals 1 plus 2 plus 3, plus 4 plus so on and so forth, N. All right, so you can see how that works out. And so what that essentially is, I got to keep touching the screen here because it dims out on me for some reason. So what that means is that the sum of all the elements from 1 through N. Okay, and then we can give another expression a little bit more complicated here. So we'll start off with the Greek symbol for sigma here. Okay, and then we'll say that this is J squared, but J is still equal to 1, okay? And then, our end, we want to get to N. So J squared would be, similar to what we saw above, 1 squared plus 2 squared plus 3 squared plus 4 squared, right? Plus so on and so forth, equal, or not equal, N squared. Okay, and then let's go ahead and map a third one here. Okay, so this will be the cubed view of things. Okay, it's getting harder to write with this whiteboard resting on me. Okay, so J is still equal to 1. That's our start. N is still our end, and then we have J cubed. Okay, and that's the equivalent of 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus N cubed, right? And so this first one here that you see, this top one here, right? This is like saying that, can you see that? Yeah. Okay, that N is N times, or N multiplied by N plus 1, okay, over 2. The second one is like saying N times N plus 1, okay, over 6 equals 2N plus 1. Right, is that coming through there for you? Can you see that? That's supposed to be a 2N. It's hard to write and make sure it's grabbing it on the camera here. Okay, so N multiplied by N plus 1 in parentheses times the expression of, in parentheses, 2N plus 1 N parentheses over 6. Okay, right, don't dim out on me, iPad. Right, okay, so, and then the third one here is like saying that N times N plus 1, okay, over 2, and overall the entire squared. Okay, so what we see in this first one is quite simple. It's old technology, right? It's called weave bowling, and so it's like if you were to put it into a geometric shape, 1 + 2 + 3 + 4, so on and so forth to get to n. It's like saying 1 + 2 + 3 + 4, right? Let's do another one, + 5. All right, and you can see how this is going. It's like a triangle, like bowling pins. Okay, and so this is, if you were to express it geometrically, is what it would look like. Now these are a little bit different geometrically. I like to, this is more like almost like a square. I like to refer to it as, the top of the cone is a square of a triangle. Is kind of like the shape here. But you can express these differently. So this is more, if you were to equate this expression up here to logic, this would be like the inductive method, right? Because you're starting from a specific, and you're reasoning your way down to the general, to a theory. Okay, so you're starting with the specific and reasoning to a theory, whereas this expression and somewhat this is more deductive in logics, and so that would be, moving from the theory itself and then trying to prove or disprove that theory by deconstructing down to the specifics. So inductive methodology versus deductive methodology. So how does that apply in economics, right? That'll be the subject of my next video and my next lecture for those on campus.